Alright, here we're looking at two charges, and we're going to let them that have an electrostatic repulsion, a 5 microcoulomb charge and a 3 microcoulomb charge, and we're going to let them repel until they're a large distance away. So we have a 5 microcoulomb charge with a mass of 1 kilogram, so let's make that him, 5 microcoulombs, and a 3 microcoulomb charge, so that's 1 kilogram. And that charge has a mass of 2 kilograms. They're held at a distance of 2 millimeters apart. 2 millimeters. And then they're let go and they're allowed to repel, so they fly off in opposite directions until they're far apart from each other. Since these two objects are going to have a distance between them that varies greatly, then if we think about the force acting on those particles, kq over r squared, since it depends on the radial distance between them, and this is going to change greatly, then the acceleration, which is equal to force over mass, is going to change greatly. And that means that our 5 equations of motion approach to this problem isn't going to work. So what we're going to do instead is we're going to take an energy approach. The energy approach is nice because we don't need to worry about how the force changes throughout the complete motion. We can simply say when they're allowed to move far apart and that potential energy is converted into kinetic energy, how much kinetic energy does each particle have? So this isn't going to be useful because our 5 equations of motion assume a constant acceleration. So instead, we're going to use an energy approach. We're going to say that the potential energy associated with the electrostatic repulsion is going to be converted into the kinetic energy of these two particles. We have a secondary issue here. Since both particles are able to move, I'm going to call this particle A and this particle B just to keep them straight. Since both particles are able to move, we're going to have a secondary issue because both of them are going to get some of the velocity, and we're going to have to get some more information to figure out how that gets split up. But for now, let's just simplify this equation a little bit. We have an electrostatic potential energy that is being converted into the kinetic energy of object A and the kinetic energy of object B. And let's plug some numbers in here and simplify this up as much as possible so that we can so that when we go and get that other equation we can get as much done as possible. 9 times 10 to the 9, that's the k value. Charge of 5 times 10 to the negative 6. And then another charge of 3 times 10 to the negative 6. All divided by the radial distance between them, 0.002. So that's in, well, we could put units in here, newtons per coulomb squared, meter squared, coulombs, meters. And over here we have 1/2. This one had a mass of 1 kilogram times the velocity squared, plus 1/2. This one had a mass of 2 kilograms times the velocity of b squared. So that's 1/2 VA squared plus 1/2 and 2 cancel out to VB squared. So that's the easy side. We'll grab our calculator here and punch out these numbers for the harder side. 9 exponent 9 times 5 exponent negative 6 times 3 times 10 to the negative 6 divided by 0.002, and I got 67.5. That would be in Newton meters. There's a Newton there, meter squared. So when everything cancels out, you're left with Newton meters or joules. And so that's an equation. We can't make this one a lot simpler. I mean, you might want to multiply it through by 2 if fractions really bother you, but really there's not much else you can do to that equation at this point. So how else can we get information about how these two objects are going to fly away from each other? Well, one thing we can do is we can recognize that if they're going to repel away, that momentum also needs to be conserved in this situation. So the initial momentum has to be equal to the final momentum. If we say they're held at that fixed distance apart, we assume that their initial momentum then is 0. So what's their final momentum? Well, it'll be the mass of object A times the final velocity of object A plus the mass of object B times the final velocity of object B. So we have most of those values. That's 1 kilogram times the velocity of A plus 2 kilograms times the velocity of B. I'll solve for VA just because it's easy. VA equals negative 2 VB. And so I get a secondary equation here based on the conservation of momentum that is going to help us see how the kinetic energy will be distributed between these two objects. So let's go over here, let's make that substitution. VA is equal to 2 VB, 67.5, 1/2. VA is equal to 2 VB. It's actually negative. Doesn't matter because we're going to square it, but just to be accurate. Plus VB squared, so 67.5 will be equal to, this would be 1/2 times 4 VB squared. Don't forget when you bring that square and you have to apply it to both things. And 1/2 times 4 is just 2 plus 1, so we have 3 VB squared over here, 67.5 joules. So divide by 3 and a square root. And I get the velocity of object B to be 4.74 meters per second. If we take that back over here, we can get that VA is traveling at negative 2 times the speed of VB, which we just found to be 4.74 meters per second. It's right here. So that means that VA is equal to 9.48 meters per second. The negative here representing the fact that these two objects would be going in opposite directions. So there it is. That's how the kinetic energy, so that's how the potential energy gets converted into kinetic energy, and how much each object gets of that kinetic energy based on the conservation of momentum.